What's up, guys? Time of flight mass spectroscopy today. This time, the calculations. Um, First of all, what equations do we need to use? So here we have, we're generally going to be given KE equals half mv squared. Um, this is easier to work with though. K equals mv squared over 2. It's the same thing. We'll need to remember velocity equals distance over time. But we can replace this v squared with d squared over t squared. And that's what I've got in this equation here. So ke equals md squared over 2t squared. And this is going to enable us to answer all of the questions when it comes to time of flight mass spec if we know how to rearrange the equation. Because generally questions are going to ask us about either the distance, the time, or the mass of a substance. We're never really going to be asked about the velocity, so this by itself is not much good to us. For now, I'm not going to really go over the reasons why. That's for a different video. But to make t the subject, we've got this equation, and to make d the subject, we make this the equation, right? So this is what we're working with. Let's try and apply it to this question. Now, perfect. We've got antinomy. We've got two isotopes here, Sb121, Sb123. Accelerated to the same kinetic energy, like we've spoken about before. The flight tube is 1.05 meters. And we're given the time for the Sb plus ion, 5.93 times 10 to the minus 4 seconds. Calculate the mass in kilograms. That's important. I'll explain why later. Mass in kilograms of a single 121 ion. And calculate the time taken for a 123 ion to travel down the same flight tube. So, straight away, as I'm thinking about this, I know I've got a lot of information about 121. I've got the time, I've got the distance, I'm going to be able to calculate the mass. I'm going to be able to work out the kinetic energy relatively easily. Then I'm also going to have the kinetic energy for 123 because that's going to be the same for both because they're given the same push by the electric fields. So then I'm probably going to use this equation to eventually work out the time taken. So I've got my plan. Let's put it in action. So first step, we need to work out the mass of 1121. And I might even work out the mass of 123 because I'm going to need that later on. So 121 SB mass is equal to our 121. The relative atomic mass is in grams per mole. I need it in kilograms, as the question says. So I'm going to divide by 1,000 and then times it by Avogadro's constant, which we're given here. If I put that in my calculator, I get an answer of 2.009 times 10 to the 25. And I might as well work out the same for 123 now because I'm going to need that later. And that's going to be the same calculation, 123 divided by 1,000 times by Avogadro's constants. And that gets me to 2.0425 times 10 to the minus 25. Okay, so let's do my calculation with respect to my 121 SB. I need to use the information I have for this to work out my kinetic energy, which will be the same for 123. So my big equation here is KE equals md squared over 2t squared. where m, we've just worked out, is 2.009 times 10 to the 25, to the minus 25, sorry. D, we're given in the question, is 1.05 meters, and I'll just check, yeah, if speed is in meters per second, my units are consistent, that's good. 1.05. And T. And T equals 5.93 times 10 to the minus 4. I'll just check my units. Speed is per seconds. We're in seconds. We're consistent. We're good. I chuck all of that into my calculator and I arrive at 3.149 times 10 to the minus 19. Now I start working with 123 SB. And this time, remember, we're eventually trying to work out the time taken. So I need this equation. So we've got T equals the square root of md squared over 2ke. Mass, we've worked out up here, 2.0425 times 10 to the minus 25. Distance, we've got the same flight tube, so we've got the same distance, 1.05. And KE is what we've just worked out. It's our 3.149 times 10 to the minus 19. And again, we put that into our calculator, we substitute our values in, and we get to a value of 5.98 times 10 to the minus 4. Perfect. Give the next question a go, using the same sorts of ideas. We'll go through that at the end of next video. For now, let's look back at our last questions. So what are the constants for our calculations? Hopefully you've seen again that kinetic energy is constant, whatever ion is there, and the distance of our flight tube is the same, right? Again, kinetic energy supplied by the electric fields, the same push is given to our ions, and the distance of our flight tube will always be the same. It's the same machinery. Next question, why does the sample need to be ionized? We've got two reasons. One is so that our sample can be accelerated. By the electric field. If it was still just an atom, it would be uncharged and so would have no effect. And two is for detection, so that a current is generated at the detector as it becomes discharged. Brilliant. See you next time. Happy revising.